Right now, your feet are slightly further from the center of the Earth than your head. It is a difference of a few billionths of a percent in gravity. You will never feel it. Your body was built for a world this gentle. But 3,000 light years from here, gravity does not whisper. It tears. Imagine you fall toward a black hole. Not quickly, slowly. Feet first, arms at your sides, calm, the way you'd fall asleep. At first, nothing feels wrong. The stars behind you start to smear into a ring of light. Your heart rate is steady. You still believe you're in control. You are not. The thing you're falling toward isn't really a hole. It's a point where the universe's rules stop applying the way they used to. Albert Einstein described gravity not as a force pulling you down, but as curved space itself, a bent trampoline sheet with you rolling toward the deepest part of the dip. Near a black hole, that curve becomes a cliff, and you're already walking off the edge. Here's what almost nobody tells you. Your feet will die before your head does. Gravity weakens with distance, fast. So if your feet are a few meters closer to the black hole than your head, they feel a noticeably stronger pull. Closer to the center, that difference stops being noticeable and starts being violent. Your feet are yanked forward. Your head lags behind. Your spine, your ribs, every joint holding you together becomes a tug-of-war rope between two versions of gravity that disagree. Scientists have a word for this, and it is not subtle. Spaghettification. Coined half-jokingly by physicist Stephen Hawking, it describes exactly what it sounds like. Your body stretches, thread by thread, into a long, thin strand of what used to be you. Not because something reaches out and grabs you, because gravity itself refuses to treat your head and your feet as the same distance away anymore. How long does this take? That depends entirely on the black hole. And here's the twist almost every movie gets wrong. A small black hole, just a few times the mass of the sun, kills you almost instantly. The stretching begins hundreds of kilometers out. By the time you're anywhere close to the center, you're already unrecognizable, fast, brutal, over before you finish a scream. But a supermassive black hole, the kind sitting at the center of galaxies like our own Milky Way, is different. Strange as it sounds, the bigger the black hole, the gentler the beginning. The boundary of no return, called the event horizon, sits so far from the crushing center that gravity barely changes across the length of your body when you cross it. You could fall through the edge of a supermassive black hole and feel completely normal. No pain, no stretching, no signs. You would not even know the moment you lost the ability to ever turn back. Doesn't that unsettle you a little? That the point of no return might feel exactly like every ordinary moment before it? This isn't science fiction. In 2019, an international collaboration called the Event Horizon Telescope did something once thought impossible. They photographed the shadow of a real black hole, sitting at the center of a galaxy called AM87, 60 million light-years away. A dark circle ringed in glowing, superheated gas. Proof, not theory. Proof that the thing devouring stars and light and time itself is not a metaphor. It's out there waiting. Keep falling. Past the event horizon now, there's no signal, no light, nothing that can climb back out to tell the rest of the universe what happened to you. Not because of distance, because the space itself is now flowing inward faster than light can travel outward. Light isn't fast enough to escape anymore. Nothing is. And this is where the stretching truly begins. Your feet ahead of you feel gravity thousands of times stronger than your head. The distance between them might only be 2 meters, but the 2 meters is now a chasm of unequal pulling. First, your legs elongate, thin, impossibly thin. Then your torso follows. Every cell in your body is being asked to occupy a space smaller and longer than it was built for. There is no version of biology that survives this. You do not explode. You do not vanish. You are drawn out physically into a ribbon of matter falling toward a single point. Physicist John Wheeler, the man who coined the very term black hole, once said that these objects teach us more about the nature of space and time than anything else in the universe. He wasn't exaggerating. Because what happens next to you isn't really about your body anymore. It's about what happens to information. Here's the part that keeps physicists awake at night, more than the stretching, more than the darkness. Once you cross that boundary, your fall toward the very center, the singularity, is not optional. It's not a place, it's a direction. In the warped geometry near a black hole, the future itself points inward. You could no more avoid the singularity than you could avoid tomorrow. What is the singularity? A point, according to Einstein's equations, where space curves so extremely that density becomes infinite and the equations simply break. Not a place with a floor, not a location you land on, a mathematical wall where our understanding of physics currently stops answering questions. Nobody knows what truly happens there. Some physicists suspect quantum effects near the singularity change everything we assume, unraveling the smooth stretching into something stranger. Nobody has ever gotten close enough and come back to check. And what about the outside world, the one you left behind? From their point of view, something even eerier happens. As you approach the event horizon, time itself appears to slow down from their perspective. You seem to move slower and slower, your image redder and dimmer, frozen almost at the edge, forever approaching but never quite arriving. To someone watching from a safe distance, you become a ghost stuck at the threshold, fading out of visible light entirely, while inside your own falling reference frame, you cross that same boundary in an instant, feeling nothing unusual at all. Two different timelines, two different truths, both correct. That is what a black hole does to certainty itself. Carl Sagan once said that the universe is under no obligation to make sense to you. Few places prove that better than the region just outside a black hole's edge, where cause and effect, past and future, stop behaving the way they do on your kitchen table on an ordinary Tuesday morning. You might wonder why any of this matters to a species living safely on a rocky planet, 93 million miles from a well-behaved, non-collapsing star. It matters because your own galaxy has one of these monsters at its center right now. Sagittarius A star, 4 million times the mass of the Sun, sitting quietly, 26,000 light-years from where you're sitting today. It isn't pulling you in. It isn't a threat. But it is a reminder. A reminder that the same physics stretching a hypothetical falling body into a thread is the same physics holding your galaxy's 200 billion stars in a slow, ancient orbit. The same gravity that would tear you apart up close is the same gravity gently keeping your solar system on its 230 million year loop around the galactic core. Violence and structure from the exact same law. There's another question worth sitting with. What happens to everything you were made of after the stretching ends? Physicists don't agree on a single answer, and that disagreement is itself remarkable. One idea, once treated as settled, is that the matter and energy that made up your body simply add to the black hole's mass, folded permanently into the singularity, gone from the observable universe forever. But Stephen Hawking complicated that picture in the 1970s when he showed that black holes aren't perfectly black at all. They leak. Slowly, over unimaginable stretches of time, a black hole radiates faint energy outward, now called Hawking radiation, and very gradually loses mass. Given enough trillions of years, far longer than the current age of the universe, a black hole can theoretically evaporate completely. Which raises an uncomfortable question. If the black hole eventually disappears, where did you go? This is what physicists call the information paradox, and it has divided some of the sharpest minds in modern physics for decades. Quantum mechanics insists that information, the complete details of everything that ever fell in, cannot simply vanish from the universe. But if the black hole evaporates into nothing, where does that information end up? Some researchers argue it leaks back out, scrambled beyond recognition, inside the Hawking radiation itself. Others suspect it's stored on the event horizon like a hologram, a two-dimensional recording of a three-dimensional fall. Nobody has proven it either way. You, in this hypothetical, would become a genuine unsolved problem in theoretical physics. Let's return to the fall itself, because there's a detail worth pausing on. As you cross the event horizon of a large enough black hole, feeling nothing unusual, you would still be able to look back. And what you'd see would not be darkness behind you. It would be light. All the light of the universe you left behind, compressed and blue-shifted into your remaining field of view, a shrinking bright circle above you as the black sphere of the horizon closes in from every other direction. Astronomer Edwin Hubble spent his career proving the universe was expanding, galaxies rushing away from each other in every direction. Inside a black hole, that expanding universe would appear to you as a single, brightening window, the last view of everything, folding smaller and smaller until the singularity finally arrives. How long would that final view last? Seconds, for a stellar mass black hole. For a supermassive one, potentially hours. Hours of watching the entire visible universe shrink into a shining point above you, while your body, still whole for now, drifts toward a destination with no floor. It's worth remembering that none of this is speculation dressed up as fact. The mathematics describing this entire fall comes directly from general relativity, published by Einstein in 1915, and it has passed every experimental test thrown at it for over a century, from the bending of starlight during a solar eclipse to the detection of gravitational waves, ripples in space-time itself. First measured directly in 2015 when two black holes collided over 1 billion light-years away. That collision didn't just confirm Einstein's equations. It let scientists, for the first time, listen to the sound of space-time being stretched and compressed by exactly the same violence that would be happening to you. So, the next time gravity pulls a pen off your desk, or keeps your coffee sitting still while you look away, remember what that same invisible rule is capable of, given enough mass and enough distance and enough darkness. It is not a background detail of your universe. It is the architecture, gentle enough to be forgotten most days, strong enough, in the right place, to unravel a human being thread by thread and erase the very difference between space and time. Right now, your feet are slightly further from the center of the earth than your head. You will never feel the difference. Be grateful for that, because somewhere out there gravity is not being gentle with anyone at all.